We'll look at writing parametric equations for curves in space, starting with that old classic, the line segment. I have a beginning point, have an ending point. I can find the vector that goes from P to Q by subtraction. 1, -4, 5. And since we're going from P to Q, I'm going to use P as my point. Pretty much if you can write parametric equations for a line, you can write a vector function. You can parameterize the line. So we'll say R of t is t times the vector plus the corresponding coordinate of the point. So for x, I have 1t plus 1. For y, -4t plus 3. And for z, 5t minus 2. Since we're looking for a segment and not the entire line, it is important to specify t goes from 0 to 1. And there it is. Suppose I want to intersect x squared plus y squared equals 1. So in 3 dimensions, this is a circular cylinder with y plus z equals 2. Well, in 3 dimensions, that's a plane. So pretty much I'm cutting a plane through a cylinder. Think about what that looks like. Here's my cylinder. It's not going straight across. Y plus z equals 2. I'm going to be coming down this direction. So my plane is going something like this through the cylinder. And we can see the curve of intersection in here. It's an ellipse, not necessarily surprising there. To write parametric equations for that curve of intersection, I'm going to notice in the xy plane, my projections look like circles. Well, I know a really good way to write a circle parametrically, and that is x equals cosine t, or radius is 1, so 1 cosine t, y equals sine t. That takes care of the cylinder part, that takes care of the circles. For z, well, I know y plus z equals 2, which means z equals 2 minus y. Well, I've already decided what y is going to be. Y is sine t. So z, 2 minus y. And that gives us this ellipse, this curve of intersection. Similar to this, I still have a cylinder, x squared plus y squared equals 1. But now I'm going to intersect it with not a plane. Z equals x times y looks like this. I'm going to spin it around a little bit so you can see. When I intersect the cylinder, it's going to go through the middle of that. So I'm going to get some kind of interesting curve that goes up the sides of the cylinder a little bit. I'm not going to attempt to draw that, but we can attempt to write parametric equations for that. Again, since cross-sections parallel to the xy plane are circles, we can use cosine t and sine t. And then z equals xy, there's x, there's y. We're going to make sure z is equal to x times y. And there's our parametric equations for that curve of intersection. We can go the other direction too. If I already have parametric equations and I want to figure out what does this look like. If I know a parametrization, so cosine t, sine t, t, and I want to think about what that looks like. Well, I'm going to recognize that cosine t and sine t for x and y are going to give me a circle in the xy plane. the z value, if I'm just in the xy plane, this is cosine t, sine t, and t equals 0. But if z equals t, that means as t grows, so is the distance above the xy plane, and I get a helix, a spiral. For the other one up there, t squared and t cubed, well, when I have t and t squared, that says y equals x squared. The y coordinate is whatever x was and square it. Well, we know what that looks like. That's a nice parabola. And then, again, in the xy plane, t cubed. I'm going to have my ends going up like this. So this is, we actually call this a twisted cubic. It's kind of cubic, but it's kind of parabolic, kind of twisted. So, parametric equations for curves in space.